Hello everyone, this is Deniz. I will be instructing the second half of the food chemistry course. We are going to start with lipids chapter. First lecture will be an overview about the definition, naming major lipid compounds, classification and introduction of some minor lipid compounds. The first thing that we want to know is what are lipids. In daily life, we always talk about fats and oils. That's the form of lipid we are consuming, like margarines, butter, vegetable oils. But lipids are not only fats and oils. There's a diverse group of lipid molecules composed of fatty acids, acylglycerols, sterols, phospholipids, and others listed here. It's a big heterogeneous lipid family. So in this big lipid family, there are major lipid compounds like fats and oils, which are chemically referred as acylglycerols, and specifically 3-acylglycerols. And there are also minor lipid compounds we can place in this big lipid circle. Minor lipids. Minor lipids like sterols, phospholipids, and waxes. They are minor lipids, but they have important nutritional and functional properties and valuable applications in food industry. So in this lecture, we will learn about these lipid groups up to here. We generally do not discuss sphingolipids in food science and technology because it's not an edible lipid fraction. It's not an important lipid in our diet. And we are not going to mention miscellaneous lipids such as fat-soluble vitamins and carotenoids here because they are already covered in other chapters. Okay, let's move on. Let's start with lipid definition. Actually, there is no exact definition for lipids due to this heterogeneity of the lipid family. There are different definitions in different books and dictionaries. Here you see how Christie defined lipids in Lipid Analysis book. Lipids are a wide variety of natural products including fatty acids and their derivatives, steroids, terpenes, carotenoids and bile acids, which have in common their ready solubility in organic solvents. So they are soluble in organic solvents. Another definition says lipids are substances which are insoluble in water and soluble in organic solvents, and they contain long-chain hydrocarbon groups, and they are present in or derived from living organisms. Let's see one more definition. And Oxford Dictionary says it's a general term for fats and oils, waxes, phospholipids and steroids. Their common property is insolubility in water and solubility in organic solvents. So when we look at those definitions, what do we see? What's in common? And especially two things are common here. First, lipids are soluble in organic solvents, and then they are insoluble in water. It's because all lipids are hydrophobic. No matter which lipid you are talking about, triglycerides or phospholipids, they are all hydrophobic. You know, hydro means water, phobic means fear. So they are afraid of water. They will repel water, which means they do not dissolve in it. As you know, water and oil won't mix. But they are all soluble in organic solvents. For example, hexane, ether, benzene, chloroform, acetone. Still, it's not a perfect definition because there are some exceptional lipids we will see later. So how do we classify lipids? Different lipid classifications can be done based on different properties and based on different point of view. For example, it can be based on their physical properties. Then we refer them as fats and oils. We make this classification according to their physical state at ambient temperature. Oils are liquid at room temperature and fats are solid at room temperature. They can also be classified as polar and non-polar lipids to indicate differences in their solubility and functional properties. Depending on the subject matter, they can be classified as essential fatty acids and non-essential fatty acids. But the best classification is done based on the lipid structure, because this contains all the lipid groups. There are simple lipids like acylglycerols or complex lipids like phospholipids, also derived lipids. Derived lipids are called derived because they generally derive from simple or complex lipids. The first lipid group we are going to learn is fatty acids. Fatty acids are the main building blocks of the lipids. And that's pretty much what lipids are all about. Remember, carbohydrates are made of carbon, hydrogen, and oxygen. And lipids are the same thing. They're also made of those three atoms. But they have a very different structure, as you can see on this slide. The structure of the fatty acid consists of a head and tail. The tail part is called hydrocarbon chain. So this is the tail part. Here you see a long chain of carbon bonded hydrogen. It's called hydrocarbon chain because it's made of nothing but hydrogen and carbons, and they are all covalently bonded to one another. And this part of the fatty acid is called the head. So the head is composed of carbon, oxygen, and hydrogen. Anytime you have COO and H together, that functional group is called carboxyl group. So the head is carboxyl group. Basically, when you have a carboxyl group end with a hydrocarbon chain together, we call it fatty acid. Let's identify the structure. On one end, we said we have carboxyl group. On the other end, we have a carbon with 3 hydrogens attached to it. Here. So it's CH3. And that functional group is methyl group. And in the middle we have a bunch of CH2 groups. They are repeating CH2 groups, maybe repeating N times. So I can write like that. On one end we have methyl group, CH3. We have repeating CH2 groups in the middle, N times. And on the other end we have carboxyl group. So that's the basic chemical formula of a fatty acid. So this N going to determine the structure and function of the fatty acid. So let's go ahead and look at the different ways that fatty acids can be presented. These are the different presentations of fatty acids here. First one is the open structure we just saw in the previous slide. If we count the carbons, we see that fatty acid has 16 carbons. So second one is called the zigzag form. This is another presentation. It's the same fatty acid, but it's presented in a different way. Here, these connections represents carbons. So these connections. So let's count how many carbons do we have. So that's the first one. 1, 2, 3, 4. And this is the last one. Again, we have 16 carbons. So that's the first carbon and that's the last one. Okay. We are not showing hydrogens here like we do in the previous one. Okay, that's the zigzag form. And the third one, let's see the third one. We can also show a fatty acid like this in the last presentation. We have a carboxyl group here. We can also write like this. Then repeating CH2 groups. N is equal to 14. Then we have a methyl group. It's important to note that carboxyl group won't always be on the left hand side. Sometimes it will be right hand side. So it doesn't matter, it will be the same structure. It can be presented both ways. It can be here or here, it doesn't matter. Okay, let's move on. Fatty acids vary in length. This is referring to the length of the hydrocarbon chain, which means carbon-bonded hydrogens. The majority of fatty acids in nature range from 14 to 24 carbons. They are called long-chain fatty acids that are found in vegetable oils and meats. If we have between 6 to 10 carbons, then we call them medium-chain fatty acids. If there are less than 6 carbons, then they are called short-chain fatty acids. Remember, in lipid definition, we said lipids are insoluble in water. And there could be some exceptions to that definition. There is one exception. Butyric acid. It's a short chain fatty acid with 4 carbons. So butyric acid is an important fatty acid found in dairy products. But it's soluble in water. So it's an exception to general lipid definition. Something to remember, something to know. Fatty acids vary in degree of unsaturation or saturation, which affects physical properties of lipids, such as melting point. Again, we have two figures. Here, this connection with red color numbers on it represents carbons. So when we say saturated fatty acids, saturated means it's fully saturated with hydrogens. The carbon is carrying hydrogen to its maximum capacity. Carbon has to have 4 bonds. So in this configuration, it's fully saturated with hydrogens. If it's missing some hydrogens, if it's not fully saturated with hydrogens due to presence of double bonds, then we call it unsaturated fatty acids. Then it will look like that. Okay. If there is no double bond, we call it saturated fatty acid. If there is like one double bond, then it's monounsaturated fatty acid. If it's two or more double bonds, then polyunsaturated fatty acid. Fatty acids can also vary in configuration. Oil processing, oxidation, and hydrogenation might affect the fatty acid configuration. The natural configuration of double bonds in unsaturated fatty acid is called the cis configuration. It's the first figure. It's natural. So in this configuration, the hydrogens of the hydrocarbon chain extend on the same side of the double bond. It's on the same side of the double bond. On the other hand, trans double bonds have the hydrogens on the opposite side, like in the second figure. Okay? Again, cis configuration, hydrogens on the same side of the carbon double bond, and trans hydrogens are on the opposite side of the carbon double bond. Most of trans fatty acids in our diets are derived from the hydrogenation process, such as partial hydrogenation. It's basically convert liquid oils to solid fats, and we are going to learn this process later in another lecture. Let's see the nomenclature of fatty acids. How do we name fatty acids? There are three different systems to name fatty acids: systematic name, common names, and numerical abbreviations. This is also called shorthand names. So those names are developed by IUPAC. IUPAC stands for International Union of Pure and Applied Chemistry. Generally, even in scientific papers, common name or shorthand names are used. Usage of systematic names are not very common. Many of the common names originate from the source that fatty acid is isolated. For example, palmitic acid. As its name indicates, it's a major component of the oil from the fruit of oil palms. But palmitic acid can also be found in meats, cheeses, butter, and other dairy products. Let's look at the numerical abbreviation here. It shows two things. The first number in numerical abbreviation shows the number of carbons here. That means there are 6 carbons in that hydrocarbon chain. And the second number shows the number of double bonds. So that's the saturated fatty acids. And you know, for saturated fatty acids, second number will always be 0. Because there is no double bonds in saturated fatty acids. And most natural fatty acids have even number of carbons due to the biological process of fatty acid elongation. where 2 carbons are added at a time. So that's why it goes like 6, 8, 10, 12. Let's look at the systematic names for saturated fatty acids. The IUPAC system names the parent hydrocarbon of the fatty acids on the basis of the number of carbons. For example, 10 carbons would be decane. Here we have hexadecane because we have 16 carbons. And the terminal E in the hydrocarbon name is replaced by oic. Let's look at the table again. We have 16 carbons. It's hexadecanoic acid. This is the systematic name. So that is parent hydrocarbon and terminal E is replaced by oic, and that's the fatty acid, 16 carbon fatty acid. So we named this in the previous slide hexadecanoic acid. So what happens if we have one double bond? Like this figure. Then anoic becomes enoic. Okay? In the IUPAC system, the anoic designation is changed to enoic to show the presence of a double bond, one double bond. So if we have 2 double bonds, still we keep the enoic and we add di here. So based on the number of double bonds, the terms goes like di, tri, tetra, and so on, like this. Also maybe penta. So it goes like that. So then how would you name it? So we have 3 double bonds, 1, 2, 3. Then it will be hexa, deca, 3-enoic acid. So we have this term here, because we have 3 double bonds. Okay, that's it. Again, this is the numerical abbreviation. First number is the number of carbons and second number is the number of double bonds. Second number is 0 because this is saturated. 1 double bond, we have enoic. 2 double bonds, we have di and enoic. 3 double bonds, tri and enoic. So by looking at that fatty acids names and numerical abbreviations, we know that if they are saturated or unsaturated. And we know the number of carbons and we know the number of double bonds. But we don't know the position of the double bonds. So for that purpose, there's another naming system. Let's see it. Actually, there are two numbering systems, delta and omega system. So the position of the double bonds in unsaturated fatty acids are numbered by the delta method, delta system, starting from the carboxylic end. It's the position of double bond from carboxylic end. And there is omega system. It's also referred as N. It's starting from the methyl end. The position of double bond from methyl end. Examples are omega-3 and omega-6 fatty acids. Let's see an example. It will be more clear for you. Here we see an example. Here you see the name. It's octadecadienoic acid. 18 carbons, 2 double bonds. It's delta 9. We can also name it again. We have 18 carbons, 2 double bonds, and it's omega 6. So how do we get that name? We said delta is starting from carboxylic end, and omega starting from methyl end. Okay? So it says delta 9. So that's the first carbon. So we go like that. 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we see that the position of the double bond, the first double bond, is on carbon 9. That's why we write this, delta 9. If we start counting from methyl end, it will be like this: 1, 2, 3, 4, 5, and 6. We have double bonds here, so we stop. Then we get omega 6. It's the position of the first double bond. Then we will have an idea. So these are the two different naming systems. If we know the position of first double bond, we write like this. Let's see the pentadiene structure. Double bonds in polyunsaturated fatty acids are most commonly in a methylene interrupted configuration, often termed the pentadiene system. So in a pentadiene system, the two double bonds would be at the carbon 1 and 4. That means the double bonds are separated by a methylene carbon. This is our methylene carbon. So this means that the double bonds of most unsaturated fatty acids are 3 carbon apart. So how can we use that information? It's possible to predict all double bonds if the location of the first double bond is known. For example, we have 18 carbons and 3 double bonds. And we know the location of the first double bond. It's at carbon 9. So we can write it like that. we know that there are 3 double bonds, and it's the polyunsaturated fatty acids. Since it has 3 double bonds, we know that it has a pentadiene structure. We can apply that rule, 3 carbon apart rule. Then the double bond positions will be, the first one is 9, the second one will be at carbon 12, and the third one will be at carbon 15. So 3 carbon apart. Okay. We can also name them like this. Let's see another example. So we can also write the cis configuration if we know it's a natural fatty acid. So that's EPA. We have 20 carbons and 5 double bonds. So here delta system is used to name the fatty acid. Remember, delta starts from counting from carboxyl group. So 1, 2, 3, 4, and 5. So delta 5. Again, because of that 3 carbon apart rule, we know that the first one is at carbon 5, and there are 5 double bonds. So we are just adding 3. So that's the second double bond, third one, fourth one, and fifth one. We can also add that systematic name. Just check the table. Let's see the table. We have 20 carbons here. So it's EPA. Okay. So you can use different naming systems based on your needs. It's another example. It's DHA, omega-3 fatty acid. Again, we have 22 carbons, 6 double bonds. If we use delta naming, the position of first double bond is at carbon 4. We can also write positions of all double bonds like this. 4, 7, 10, 13. Oh, it's missing here. It should be 16 here. And 19. Okay, let's move on. So oils and fats vary widely in fatty acid composition. Vegetable lipids predominantly contain unsaturated fatty acids. Most vegetable oils primarily contain carbon-18 series fatty acids. Olive oils and canola oils are high in oleic acid, which is 18 carbon, 1 double bond. Corn and soybean oils are high in linoleic acid, 18 carbons, 2 double bonds. And linseed is high in linolenic acid, 18 carbons, 3 double bonds. On the other hand, animal lipids contain higher levels of saturated fatty acids, with palmitic acid and stearic acid being the major fatty acids. Okay. Another lipid group is acylglycerols. You learned that fatty acids are the main building blocks of the lipids, but free fatty acids are not common in living tissues because they are cytotoxic. they disrupt the cell membrane organization. If these free fatty acids are esterified onto glycerol, their surface activity decreases. Therefore, their cytotoxicity decreases. Over 99% of the fatty acids in plants and animals are esterified to glycerol to form acylglycerols, which are the predominant constituents in oils and fats. If three free fatty acids are esterified onto one glycerol, we call it triglyceride. This is glycerol, and we have three fatty acids, 1, 2, 3. And this is diglyceride. Glycerol, 1 fatty acid, and second fatty acid. Another diglyceride, 1, 2. If we have just one fatty acid, then we call it monoglyceride. Let's see the esterification reaction. This is the esterification reaction to form triglycerides. Triglycerides are the most common type of the lipids, fats and oils. These are the foods that you eat: butter, margarine, olive oil. These are all triglycerides. And this is glycerol molecule. It has 3 hydroxyl groups. Three fatty acids are esterified onto glycerol. They can be the same fatty acids or different fatty acids. Then triglycerides are formed. As the name says, they are 3 esters of glycerol. We can show it like that. We have a glycerol, and 3 fatty acids. So what happens if we break down that structure? So complete hydrolysis of triglycerides yield free fatty acids and glycerols. It's an hydrolysis reaction. A lipase is an enzyme that catalyzes the hydrolysis of fats and oils. If we hydrolyze triglyceride by using lipase enzyme, we get diglyceride, 2 fatty acids. If we hydrolyze more, then we obtain monoglyceride and 2 fatty acids. Sorry, this is 1 fatty acid. And complete hydrolysis, we get 3 fatty acids and glycerol. So that's the process. Let's look at the triglyceride nomenclature. So this is a triglyceride with 3 fatty acids. The central carbon of a triacylglycerol exhibits chirality if different fatty acids are present at the terminal carbons of the glycerol. Because of this, the 3 carbons on the glycerol portion can be differentiated with stereochemical numbering. According to stereochemical numbering, they go like SN1, SN2 and SN3. First fatty acid is esterified to SN1 position. Second fatty acid is esterified to SN2 position, and third fatty acid is esterified to SN3 position. So carbons of the glycerol molecule with a specific names. So triglyceride can be named based on the position. SN1, SN2 and SN3. Let's see. As an example, we have a heterogeneous triglyceride here. It contains palmitic acid, oleic acid and stearic acid. Triglycerides that contain different fatty acids are named differently depending on whether stereospecific location of each fatty acid is known. The nomenclature for these heterogeneous triglyceride replaces IC at the end of the fatty acid with name OYF. If the stereospecific location is not known, a triglyceride containing palmitic acid, oleic acid and stearic acid would be named like this. Palmito, oleo and stearin. If we know the stereospecific location of the fatty acids, then we can name the triglycerides like that with the SN numbers. Also, these triglycerides can also be named using fatty acid abbreviations. P for palmitic acid, ST for stearic acid and O for oleic acid. And you can always use numerical abbreviation if you don't know the stereospecific locations. So there are different naming systems for triglycerides. You can choose one of them. If triglyceride contains only one fatty acid, for example just stearic acid, it could be named 3-stearin, 3-stearate or glycerol 3-stearate, or we can just use again numerical abbreviations. So you can use different names for the same molecule. Okay, let's move on. Another food lipid class is phospholipids. This is one of the major polar lipid groups. Phospholipids are used in many food formulations. They are good emulsifiers, like lecithin. Let's look at the composition. It's similar to triglycerides. There's a glycerol backbone here. One fatty acid is esterified here, the other one esterified here, and that's the third one. But the third group contains a phosphorus group here. Instead of a carbon, we have a phosphorus. P, phosphorus group. And there is one X here. It represents a functional group. And the name of the phospholipid comes from this X group, this functional group. For example, if X is an hydroxyl group, then it's called phosphatidic acids. So depending on the functional groups, there could be phosphatidylcholine or phosphatidylserine. Okay? That functional group makes the difference. So where can we find phospholipids? In milk lipids, there is around 95% triglycerides and only 1% phospholipids. But egg yolk is composed of 66% triglycerides and 28% phospholipids. And when we look at the composition of phospholipids, we see that the major one is phosphatidylcholine with around 73%. And there are different kinds of phospholipid groups. As you see, egg yolk is a rich phospholipid source. Let's look at the sterols. Sterols are derivatives of steroids. They can be derived from plant or animal sources. One example is cholesterol. I think we are familiar with it. It's the major sterol found in animal lipids. So they are non-polar lipid groups. They are composed of 6 carbon rings. Hydroxyl group at carbon 3 makes these compounds surface active. This hydroxyl group makes it surface active. Therefore, cholesterol can orient itself into cell membrane, which helps stabilizing membrane structure. And here is the sterol content of different fats and oils. As you see, they are minor lipid components and found in very small percentages in fats. But they are very valuable. And final lipid classes are the waxes. Wax is an ester of fatty acid and a long-chain alcohol. They can be classified according to their origin. These are animal waxes like beeswax and plant waxes like carnauba wax. They found on the surface of plant and animal tissues to inhibit water loss or to repel water. That's why they are commonly added to the surface of fruits to slow transpiration of moisture losses during storage. An example can be coating apples with wax. Producers spray the apples with a thin layer of wax to prevent such moisture loss, as well as to make the apple look shiny, which is more appealing. Okay, this is one food application. That's all for this lecture. Let me know if you have any questions.